In speaking of nanotechnology, we often talk about the size of things. It takes a billion nanometers per meter, and if you were to sit down and count them, it would take you 30 years to get to the other end, and so on. But when one is actually working with it, you don't think so much about the comparison of that size to our familiar large size, but instead a comparison to familiar nanoscale objects. We all feel that we have some sense of what DNA is. It's a molecule with size and shape and function, and it's about 2 nanometers in diameter. And the reason we care about it is because of what it does. Well, likewise with nanoscale machinery. Here's a device shown to scale. We have DNA today. We can synthesize DNA. We can even build with DNA. But there's a long technological path, long in the sense of a number of steps, possibly not so long in terms of time, that leads from today's atomically precise molecules like DNA to structures like the one on the right. And what I'm going to be discussing is what we can do with structures like the one on the right. That, by the way, is a planetary gear, speed reduction gear. It has the same function as gears that are found in the transmission of an automobile, despite being about 1,000,000 times smaller. So, 3 areas: nanoelectronics, nanomachinery, and then how those lead to reshaping the 21st century. Later on, I'm going to come back after talking about the fundamentals, the foundational technology, come back and talk about applications. And these are some of them. Electronics, which is very different from spacecraft and spaceflight, which is very different from the esoteric problems of quantum computing, which is very different from global energy supply, which in turn is very different from medicine. So how can all of those be changed? By one transformative technology. Most people find that idea rather surprising, and for good reason. In history, we don't very often see that quality of technological change. So imagine that I got up here, and it was the 1950s, and therefore I don't have any of the equipment that we're using here and so on, but imagine. And I tell you that I'm going to give a talk about a transformative technology that is going to change the foundations, fundamentally transform photography, and mail, and games, and television, and music. And then I add to that maps and movies and audio tape and shopping and telephones, and the question would be, how can that possibly be? You look at these, they're very different pieces of hardware. They serve very different functions. They vary from devices full of electronics to pieces of paper, through places where you put something and a person comes along and picks it up and carries it away. Those are all very different, and yet we know that one technological revolution has transformed and is increasingly replacing all of those. The prospect in the 21st century is for a transformation that is equally broad, equally profound, not in the world of information, but in the world of physical objects. And I'm going to describe why that is and outline how. So an important fact that I think it would be helpful for people to recognize and to change their language a bit is to recognize that the information technology revolution is a nanotechnology revolution. We're using nanoscale electronics. Moore's law, which gradually took this chip technology down from the scale of microns to nanometers, a factor of 1,000 in linear dimension, a factor of 1,000,000 in area, devices per area. The Moore's law revolution is a revolution in manufacturing. Our world is being transformed by a nanotechnology, and I'm going to be pointing out a deep analogy between that and the next revolution. But first, a comparison of the physical nature of these things. Contrast between machines and the nanoelectronics. Nanoscale electronics today is made by multi-billion-dollar fabrication facilities. Intel raises enormous amounts of capital, builds enormous physical plants with very large, expensive machines that reach down into the nanoscale using optics, light, chemical and material processes to make structures like the one that's shown here. It's got components that are small compared to 100 nanometers, which according to official definitions makes it nanotechnology. Those parts are rough and irregular, which is fine, because electrons don't care about whether the surface of a wire is rough or not. They flow through the interior. But if you look at the upper left-hand corner there, you'll see a little white rectangle, and in the middle of it, a dot of color. And if we zoom in on that, we have an image, roughly to scale, of a typical, qualitatively typical nanomachine. And each one of those little spheres is an atom, Each atom is in a precise location, and working together they provide a regularity, a surprising smoothness of motion that is essential to nanoscale machinery, but not essential to electronics. So atomically precise fabrication, atomically precise machinery is essential here, and that is the reason why there has not been a smooth path of miniaturization leading to this technology. It's different. It has to be built from the bottom up, from the atomically precise fabrication we have today, which is in the molecular sciences. The central technology here is one of machines. And one of the surprising developments in understanding this area is to realize that machine technologies scale all the way from the macroscopic range, where features are measured in centimeters and millimeters, down to the nanoscale range, where the parts are atomically precise. And what do I mean by machines? Well, on the upper row are a couple of components that you might find again in automobile transmission, and below are functionally identical nanoscale structures, similar in shape, identical in function. The difference is that the gear teeth are rows of atoms, and the bending joints are rows of molecular bonds in the lower right. So form follows function. And if you give engineers components that have a certain form and a certain function, they could build with them. Now, what can we build with this nanomechanical technology? Well, we know a lot about that already. You can build machines. Machines like the ones that we build at a larger scale. Okay, so you have hundreds of years of mechanical engineering experience figuring out what can be done with gears and bearings and hinges and conveyor belts and motors and all the other basic components that are used to make things like factories. So if one can make machines on a large scale, a medium scale, and a very small scale, there's a spectrum of technologies that goes all the way from the atomic or molecular scale to the macro scale, with machines all the way through that can be designed by mechanical engineering techniques and computer simulation. So here's a machine. This is a bit of video from the Tesla factory. And you see a machine that contains, gears and bearings and all that sort of thing. And those have been put together to make something that can move things, pick and place and assemble smaller parts into larger parts, in this case, a completed automobile. So how do we bridge from the nanoscale to things like automobiles? It's a fundamental scaling law which comes into play here. You might think that the very small machines can't do much because they don't move very much around and they're very small. But size times frequency is a constant in machinery if you scale them in a reasonable way. And that means that if you make something half the size, the frequency doubles. 1/1,000,000th the size, and a machine can do 1,000,000 times more cycles per second compared to the larger machine. Bridging from one scale to another, we start thinking about the macro scale. We're making automobiles, so we take automobile-sized parts and put them together to make automobiles. Now, if you're going to work from bottom to top, starting with very small parts, then the right way to make these relatively large parts is to put them together from smaller parts that are assembled by smaller machines that work at higher frequency. Well, where do those parts come from? Well, they're put together by smaller machines that work at higher frequencies, that have large numbers of them, and they get their parts from yet smaller machines. And that story goes all the way down to the nanoscale. So in a factory with this architecture, what would you find at the bottom? Well, you'd find nanoscale machinery built to atomic precision and moving molecules, where the parts are prefabricated by nature. They're perfect. Atoms are all perfect. Molecules that are made in a precise pattern are perfect, all the same. And therefore, a very regular process, a very regular kind of machinery, can operate on these and put them together as building blocks. So zooming in here, we see molecules, those are acetylene molecules, being bound by a machine, and machine components coming in, grabbing them, making a chemical transformation. Further transformations produce pairs of carbon atoms that are very, very eager to bond to something else because they've been stripped of hydrogen, and they're put together to make little blocks. And you can think of those as Legos. The molecules are like very small Legos, and you take the small Legos and you put them together to make larger Legos, which can be put together to make larger Legos, and so on. So at the very bottom of a process like this, you find atomically precise machinery putting together molecules. Machines all the way down. So I'd like to stop for a moment and make a more abstract comparison. We have the first great nanotechnology revolution, nanosystems, which is nanoelectronics, and the second, which is nanomachinery. So in both cases, we have billions of devices working together. Chips have billions of transistors. They do something with discrete universal components, and they do some kind of general purpose processing. But in the case of information processing, we use electronics. In the case of processing matter, you have to move things around. That means you need machines. Universal components, bits and bytes. It's what's enabled us to have information systems that can do, in some sense, anything, because it's all about making patterns of those little elementary components. Similar story, but with atoms and molecules. General purpose processing. In one case, you put out under programmable control patterns of information that can then turn into images on a screen, or video, or sound. And in the other case, patterns of materials, directly useful physical objects. And so, from the information revolution of nanotechnology today to the production revolution of nanotechnology tomorrow. An analogy is a 3D printer. It gives us a taste of where this is going. Desktop-sized machine can make tangible objects large enough to hold in your hand. How does it work? Download a file, description file from the internet, load it up with raw materials, let it go, moves around, puts together little dabs of material, can make more or less any pattern, and out the other end comes an intricate object. Now imagine being able to do that much faster because there are arrays of very large numbers of machines working at very high frequency, not making things of plastic or metal, but super materials, atomically precise materials as strong as any that have been made in the laboratory, and devices like nanoscale electronics that is beyond the state of the art today because you can make smaller, more precise structures. So a desktop machine that can produce, for costs on the order of raw material costs, about $1 per pound, among other things, electronics that is better than what Intel can do with a $1 billion fab. Being able to make, for example, a laptop computer that contains 1 billion processor cores. So let's now ask what that kind of capability can do when applied on a large scale in the world. And I think it should be clear that this kind of technology could be applied on a large scale. Electronics. Well, I've explained how this can push past where Moore's law has taken us to a far more powerful kind of information processing electronics. Spacecraft. I mentioned super strong materials. Well, you can make materials that are something like 50 or 100 times the strength-to-weight ratio of what they built the space shuttle out of. It's much easier to get to space if your vehicle is lighter. And the cost of making space hardware today is in the range of thousands of dollars per pound. It looks as though that can be dropped to something more like $1 per pound. And the prospect coming out of that is of being able to open the solar system to human access in a way much like the way that sailing ships opened the Earth to exploration and settlement centuries ago. Quantum computing. Well, I simply say that putting all the atoms in the right place turns out to be very important to a wide range of quantum computing schemes. In fact, people are already doing that in a limited way, putting phosphorus atoms one by one in place in silicon crystals. Energy. Well, photovoltaics are very attractive. They're getting better. They're getting less expensive. But if you could produce very high quality materials at very low cost and supporting structures at very low cost, then the cost of solar photovoltaic energy can be dropped by a very large factor and production can be ramped up enormously. So the prospect there is for capabilities that can address global energy problems. Likewise, transformation of electrical energy into chemical energy and back again, you might guess that that can be done rather well with nanoscale machinery that works with molecules. So, medicine? Well, our bodies are full of intricate molecular structures that are built by molecular machines. States of ill health are really derangements or misarrangements of these structures. The difference between a regular cell and a stem cell is throwing some switches that are molecular switches in the nucleus. The difference between a cell with a mutation and a cell that is fresh and undamaged is a matter of editing DNA. And to have the ability to make nanoscale machinery that can interact with biology and with the human body at the scale at which things are happening, at the molecular scale that is the natural scale of biology, clearly opens new horizons in medicine. And it's hard to say where the limits of that are, but they're extraordinarily broad. But there are problems on a larger scale in the world. Energy addresses one that's global scale. Another is mineral resources. It turns out that the nature of this technology is such that you want to use different materials. And those materials turn out not to be the scarce metals that people are moving into a geopolitical conflict about in Africa. They are common materials, things like carbon, oxygen, nitrogen, silicon dioxide. Can do pretty much anything you might want with little pinches of some other materials. Water. Well, that's a manufacturing problem. The oceans are full of salt water. To get fresh water is a matter of having the energy to do the reverse osmosis, filters and systems for cleaning the filters to do reverse osmosis, and then having the pipes and pumps to distribute the water across continental distances. People looking at strategy are expecting to see growing conflict in the world over water. It's a manufacturing problem. Agriculture. Can increase the yield of agriculture by a factor of 10 if you can afford to build enclosed greenhouses. That can reduce the footprint of the human race on the Earth's ecosystems and forestall food shortages for generations. Poverty and development. Well, why do countries want to industrialize? So they can make things. It's a manufacturing problem. New ways of making things can raise the material standard of living of people around the world to a higher standard than we have today and with less environmental impact, if you have a scalable, high-performance manufacturing technology. Finally, a few words about climate change before I wrap up here. Climate change also can be construed as a manufacturing problem. So today, CO2 levels are going up because of our energy systems, being carbon intensive. Replacing those with renewable energy would do something like this. CO2 levels would remain high, start to decline slowly, very slowly, and the polar ice caps would continue melting faster than they are today because the CO2 levels will be and would remain for a long time higher. So it's a very pernicious problem, very persistent. What you'd like to have is a future with negative carbon emissions that can take the levels back down to pre-industrial levels or whatever seems desirable in a rapid period. That takes a lot of energy. 10 to the 21st joules, that's 3 terawatts for a decade. That's as much power as the human race consumes in the form of electricity today, total. Our industrial society today can't afford to fix its own problems. But with the next generation, a post-industrial manufacturing, the prospect is being able to afford to build the photovoltaic arrays and the equipment needed to do the thermodynamic work of compression, to take the CO2, put it in packages, and take it away. Array area, about equal to the green square there, total aggregate area needed. So the prospect is both for a lot of cool tech, improvements in medicine, and solving a wide range of global problems. And if you consider the kind of future that people are expecting today, one of scarcity, one of conflict around scarcity, one in which Earth's climate may change in a way that destroys ecosystems from poles to equator, what we're looking at here is the potential for a different kind of technology leading to a different kind of future. There are concerns about disruption, misapplications of the technology, but the basic message is one of the potential for solving the great problems that have been darkening our future. The potential is to have a very bright future, one that fulfills some of the dreams of previous generations that have been abandoned. So, if you'd like to dive deeper in this subject, I went to Oxford to finish this book. It came out last year, decided I liked Oxford and have stayed there. And this goes from foundations that I described all the way through issues of public policy and strategies and national interest, as well as development pathways. Thank you.
You know, when you think about it, I mean, today is a great time, you know, in history, really to be alive with all the things that are happening. When you consider the last 20, 30, 40 years, the inventions of things like the chip, software, storage, the internet, and what it's caused. I mean, if anything, it's brought an incredible acceleration of invention that has never been seen before, to an extent today that all the pundits, and you've heard it today, you've heard it previously, that more will be invented in the next 10, 20 years than in the history of mankind. And when you think in terms of nanotechnology and things like this, it's really not hard to believe that that's the pace we're on, which is an incredible pace. When you look at the revolutions going back a little bit, like the revolution called the Industrial Revolution that we all studied growing up in school and so forth, which was really precipitated by the invention of the machine. And with the machine, even maybe more importantly, the assembly lines. And now you're hearing about things like self-assembly and self-replication and robots and so forth. But that was an amazing time, as so was, in the last 20 years, the digital revolution, with people like Nicholas Negroponte writing things like Thinking Digital and the digital re-architecting of everything. And I spent a lot of my life in that space where, you began to see literally a digital divide take place between the analog world, the digital world, and it took place in sometimes a day. And it continues to move at that pace. And so now we reach this next revolution, which is the nano revolution. And it is truly phenomenal when you consider on the right, and I used to be at a little company called Motorola, building cell phones and things. And what you're looking at on the right, you couldn't see with the naked eye, but it's a gear assembly inside a cell phone, smartphones. These smartphones you use that over the last 10 years, we've been able to cram what was 80 pounds, or at one point 2,000 pounds of material science into a little few ounces, so that you've got cameras and recorders and all these other kind of things all stuck into that little device. And so while that may be exciting to look at that, that's about 10 years old. So nanotechnology didn't just happen yesterday. It's been going on for about 30 years, but it's moving at an incredible pace now, more than ever before, for a couple of reasons. Number one is that we now have the instrumentation to make that happen, that didn't happen until really recently, to work at the atomic scale, to work at the molecular level. We also have universities around the world that are moving at an incredible pace to create their nano departments that are maybe their most funded departments, that are creating human intellectual capital to deal with these things, so that when I build a company, I can bring in scientists that are from interdisciplinary sides in chemistry and mechanical science and physics and so forth, bring them all together, that are nano-trained and understand how it is to invent at nanoscale. And we all had microscopes growing up, but that area more than anything else is lending itself to nanotechnology, to where we can accelerate at incredible speeds, as we have things like electron microscopes, where we can really not only envision but see what it is that we're building and how we're building it, and be able to manipulate matter at the atomic level, really, every day, day in, day out. Create the invention, and then begin to make it self-replicate and do other things. It's just a thrill to be here, and especially see the astronomy and what's going on, because this is a Hubble telescope shot, and just to see how big the universe is. And so, it's real easy to see the universe and to think of the universe. If I held my hand out at 4 feet and doubled it, and I got to 1 million miles, 2 million miles, 100 million miles, we all have seen the Hubble telescope. So it's easy to say infinite. It just goes on forever. But if I were to take my hand out here and say, okay, let's divide by 2 instead of go times 2, and I'm here 1 million years from now, right here, we still haven't hit the bottom, okay? We still haven't hit the bottom. And so there's equal universes in both directions, and that's something to really appreciate, because now you're looking at the nanoscale, which looks a whole lot like the one I just showed you, which was looking up. Now I'm looking down, and this is a brain cell. And this is where we operate, in totally different universes that are available to us today. We don't have to send anybody out to space. We just have to get on the electron microscope and begin that form of invention. So in the curiosity way, let's dive deep for a second, because I want to really translate this for you. And we'll start with the American Standard of Measurement, which of course is the yardstick, albeit in nano we deal in metrics. And nano is really a metric. It's a billionth of a meter. So we know what a centimeter is, 100th of a meter, which is a B. The width of a B here at 100,000 nanometers. We're making things inside our factory every day at 10 to 80 nanometers. One bacteria, 1,000 nanometers. When you get down, you sneeze, virus, 1 million viruses come out at about 100 nanometers each. Again, we're building stuff at 20 to 80 nanometers. The carbon nanotube, one of the first rules of invention, and now half of a DNA helix at 1 nanometer. and then the atom, which is at this point 10 times bigger than nano. But just to scale that for you. So I think if I were to build this and say build it at a yard scale, it's not going to be much of a podium, but at an inch I can make this really nice. At a nanometer I can make it last forever. So it's a lot like what we just went through, which you just saw right there on the top. We had the digital revolution, moving analog to digital, and what it did, for all of us in the room that saw the incredible digital divide that took place and how much better with ones and zeros we were able to do things as opposed to in the former, the analog. Now as we move from micron to nano, you're going to see the same type of divide, and it's going to happen, I believe, a lot quicker. If you thought it was quick with digital, watch what happens with nano in the material science area. Material science has led to most all the inventions that we know of, and ages have been named after material science. So obviously over here you see the wheel of invention over there. The wheel was a material science invention back in the good old Stone Age, and then we moved into really great inventions with pottery and jewelry, and even things seem to always do, they go to weaponization with body armor and then tools, and the next thing you know we had manufacturing plants moving very fast here, and cars, and then the last 100 years, which we can all kind of look back on and say maybe that becomes the Silicon Age. But without question, what you just heard from Dr. Drexler is not only going to happen, it's already happening, and that's this nanomaterials age as it moves. So it comes in all shapes. In the past when we built things, we always heard of building blocks, and we were really restricted at the end of the day. And so, this is all nano, so it's a whole new form factor. A whole new form factor. Remember Steve Jobs talking form factor. But this is at a scale like never before to build things better. So basically, everything that does get built can be built better. Now, we're not alone in this game. We're actually in the moon race, a bigger moon race than we've ever been as a country in the United States, because what we're able to change with this will make that country more competitive overnight. So you see the billions that are going into nanotechnology, and you see the forecast to the tune of $3 trillion in products by 2015 that are nano-enabled. But when you look at even our government today, every single agency, through the National Nanotechnology Initiative, are engaged in a big way. And so far, we've spent $20 billion over the last since 2001 to increase nanotechnology in the U.S. And so, so you don't start saying, well, that's a lot of money, and where is it really going, and everything. It is not just us. There are these countries called China that are building these massive nanopolises just outside of Beijing, and that, by the way, was provided me about 3 years ago by the FBI, who visited us one day and said, we're going to be looking out for you to protect you on your firewall, because we see it being hit every day about 1,000 times by the Chinese military. So these guys are really taking it very, very seriously, and they realize what can be done with nanotechnology to be competitive. If you thought they were competitive in solar, if you thought they were competitive in doing other things, watch what happens in nanotechnology. So we're not alone. Rust Nano in the United States has a $10 billion fund today. They go literally company to company to try to either make an investment, get on the board, catch up with all our NSF, NIH-sponsored programs to the tune of billions of dollars that have come through the universities and are now moving out into the real practical world of factories and plants. And they visited us too. I just didn't take their money. This is all out there today. No different than the glasses I'm wearing today have a nano coating, and probably all of yours do, if you said, can you make these scratch resistance? And that's been going on for about 10 years. But nano tagging, it's going to be a lot harder to steal things in the future, I can tell you, because of the ability to nano tag every part with millions of nano tags, and you can't see any of it. And so at the bottom, it's the same thing in pharmaceuticals, so that if you know where that came from, the day it was made, where it was made, what's inside it, and is it really legal? Our money itself, if you've seen the new bills, they're just changing rapidly. Why? They're trying to avoid counterfeiting. The way they do that, nanotagging. Nanotagging inside those bills every day. So down at this world of where we're able to manipulate, make atoms literally work harder and smarter, this really truly is real, and thanks to Louis Schwartzberg, who's done an incredible representation here of how that's done probably looks a little difficult here, but it moves into things like medicine. We don't talk a lot about it, but it's coming at an incredible speed, and that is the ability to do things like if you want to literally go to the DNA level with these molecular machines and fix things that have never been able to been fixed, even at the nerve tissue before. These molecular machines are coming at a speed you just would find probably not even believable right now. So when you hear words like nanobots, there are companies out there today that are literally making these things so that they can literally be put into your body either by breathing it, injecting it, drinking it, and what have you, literally clean out your vascular system and do all kinds of other things. Instead of chemotherapy that kills the body to kill one tumor, go attack that tumor. So at this scale, by the way, they're not that big, but at this scale, we're really basically creating artificial atoms and being able to control those either through laser or through magnets to where it goes to the exact spot and administers what it needs to administer at that point. That is not that far off at all. So while we're talking about futures, let's go back in time a little bit. You know, good old Leonardo da Vinci. A lot of what happens in nanotechnology, because at this scale, you're down at the human nature, or some people say the God scale, to the extent that you can manipulate things, make things better, repair things, and so forth. In the early days of invention, remember these drawings from Leonardo in the late 1400s, early 1500s, where it's called mimicry or biomimicry, where we literally take those things made by nature and either match them or improve them. And a lot of the ideation where we get this invention is, in his case, the wing that he said, you know, that's a bird wing, that's how we'll fly someday. And it's gone so far that literally all the designs by Boeing, by others, all the way back to the Wright brothers, have used that biomimicry. But in the future, at a speed you can't even imagine, organizations like NASA are looking at creating wings that morph. At the scale of nano, creating feathers on those wings, just like eagles have, to where they're like different types of trim, you know, and literally have the ability to morph in flight and take away turbulence and provide all kinds of new competitive ways to fly and decrease fuel consumption and things like that. And it'll only be through nanoscience, the coatings, the lubricants, and things like that are coming on the market already that'll allow us to do these type things. So, you know, let's get a little pictorial here. So we all have seen chameleons before. This is a super chameleon, by the way, so you'll like this. And they're really able to do these things. So this is real. And you know, the question is how. You know, so and this is biomimicry at its best. And this little fella right here is going to show you how it's done. So how does that happen? Well, when you put him under a microscope, you begin to see things like the fact that he has a translucent skin, and he has 3 layers of cells underneath that. And those cells are manipulated at the atomic level by him. He doesn't know how. And it allows him to turn colors. And in science, when we take that and say, okay, we can do the same thing with our cars, with our paint. Let's just take the same type of method, the same type of cellular representation, and do it at literally atomic level, so that if I don't like that color of my car in the morning, I just take an electrode and I hit it. And just like the chameleon, you know, I take the purple version, okay? And if that didn't work, I'll go get like those lime sunglasses the next day that. So this is where it heads, because at this cellular level, you're able to do things like this, like what was described by Eric. What a great guy. Everybody loves dogs, and dogs have a competitive advantage over humans like nothing else, one of which is their nose, their ability to sense. And that's why when you're walking through airports and things today, you see those inspections by a nose that's the best nose in the world. But we can't, in the world that exists today, just get these dogs out there fast enough and in places, and we might even be able to improve the sensor receptors of that nose. But you'd have to go down to the nanoscale to really see those receptors and to see how those receptors operate. And when you do, you come up with things like this, which is real and is going to market right now in a big way. And they're going to end up in everything, including suitcases and on walls and in buildings and so forth. And it's basically an electronic nose, except it has sensor capabilities even beyond that Labrador. And that's happening today, but only through nanoscale can you do these type of things. Look at nature and look at the amazing feats, because when we're in that ideation process, moving to that invention process, it's always amazing how we see it first with the animals. So this gecko, which can go right on glass. Robert Full did a great piece of work on this to show how those geckos have the ability with their feet to climb. But when you put it under the microscopes and you really dig deep into what it looks like, you begin to see these ridges that you know, and you start thinking in terms of suction cups and stuff. And then as you go deeper, you find out there's millions of hairs inside those ridges that operate in a certain kind of way that actually allow you to do that and carry enormous amount of weight, but only, again, at that incredible electron microscope scientific scale can you see that, and then begin to build the machines. And then at some point in time, put it even in gloves so that we all get to do what this guy got to do in his movie, and we make it real. And this is innovation at the nanoscale. So those gloves are already out in the military. They're already used. Some things can't be shown under non-disclosure, but it's happening at that kind of pace. Go back in time again, when Da Vinci was trying to scale out and literally do the ergonomics of everything. This has been used to move us forward in terms of biomimicry. You see our soldiers coming home, and you see things like this, which are incredible. Some of this is nano, some of this is just basic you know, mechanical engineering, and fantastically done, so that soldier can now move and pick up things. But through nanoscale, through sensors, and through literally hair-like, below hair-like size, you know, on the fingertips of that, we can now create, connected through nano connections to the nervous system, the sense of feel again. And so these are truly, truly amazing. What's this old guy got to do with nanotechnology anyway? Think about it for a second. I don't know what's going through your head, but there's a program that's been going up at the University of Alaska, and it's a really neat program. Because at the nanoscale, we can extract the chemistry after taking incredible electronic devices and studying the hibernation habits of a bear. When he goes through this process where he drops his heartbeat from 300 beats a minute down to 8 beats, 11 beats, 12 beats, whatever, a minute, and we can study that. And then you can get inside the chemistry of that incredible nature phenomena. And when you do, and if you've got the assignment from NASA, like they did at University of Alaska, to try and figure out how do we do suspended animation? How do we really get somebody to Mars? You suddenly realize that you can take that chemistry, and that bear, when he wakes up after 6 months, 4 months, 8 months, whatever, is able to remember when he walks outside that cave. If he goes left, it's 600 feet down. If he goes right, it takes him into the valley to forage food like he always does. And when he wakes up, there's no atrophy, okay? And how does that happen, really? And only through literally the miracle of nanotechnology can we do that, leading to things like this, that perhaps are not only for space travel, but to put you in that position, drop your temperature just like a bear's drops through the virtue of nanotechnology, while we wait to fix you at a hospital. Not very far off, not very far off. Or we learn how to inject that and do it in a way so that we literally atrophy that tumor, put it to sleep, make it go away. So this is all coming at incredible speed, and it's not going to be just for, you know, stuff for consumers to use and so forth, and for the doctors to use. Everything in technology always moves to, of course, weaponization. And we're seeing it more so in things like UAVs than probably anything else today. And frankly, the country with the best UAVs wins. It's no different than the cowboys and Indians. The Indians could outride us, they could outfight us, they could outrun us. They had bows and arrows, the other guys had guns. No place more than UAVs are you going to see nanotechnology in weaponization. So, you know, they're not all one size. They're coming at us at a speed that, you know, they're now being sold in the malls. Kids are using them. The FAA is having to get involved real quick, like, because we've got to restrict this to 400 feet. But they're getting really, really small. And this is from DARPA on the right. You guys have probably seen that. That flies about 18 hours, the one on the right, and it can hover, it can go forward, it can go backwards, and it can fly about 18 miles on one single charge. And so, by the way, when they run out of charge through nanotechnology, what do? Just go land on a power line, recharge. And so that's coming to your neighborhood real soon. Now, if you didn't get scared about that, this might take you to the next level, because they're going to get smaller and smaller. So you notice on the tip of this one is a hypodermic needle. So depending on what the mission is, fly around, get a little DNA, and from 3 miles away, take the shot. Or it can have an entire infantry coming at you, and you can send what's called a swarm of them, and just say, nick them, put them to sleep, we'll take care of the rest. And they don't have to have somebody back there with a joystick flying them, because where this technology is going through people like the folks up at the University of Penn and Dr. Kumar. You can see what's called autonomous and semi-autonomous flight here. So these are all being controlled. They're in formation. You'll see a figure 8 in a second, and so forth. And so if you didn't think this was just around the corner, it really is. And if you look up in a second, you'll see actually the radios and the things that are controlling all of these without one guy controlling the entire force. This is definitely a swarm. And these can be weaponized. They can be taught to play an orchestra, to lift things, move things around. They can be brought into buildings so that your son, daughter, whatever, if they're sweeping a building in enemy territory, they can do heat censoring and all that. So all that stuff we've seen in movies, it's here, folks. And it's coming at an incredible speed. But if you're going to have your house appraised, this is another way to get your house measured as well. So, you know, these guys really aren't aliens. Some of these are bad guys, some of these are not so bad guys, and some of them we need even to live in terms of bacteria, and we need to be able to pick the difference. And so, you know, at our company, one of the things we do is we have a thing called InGuard, and the first thing we did this for was the soldiers, because their body armor, they're out in the field, and they're constantly just being picked up with and getting nicked, and one of the worst things they bring back are incredible diseases, skin diseases. So they want uniforms that do all of this, antibacterial, antimicrobial, anti-mold, mildew, which turns into all kinds of bad bacteria. Take out the bed bugs, the sleeping bags, the tents. And also while you're doing it, Jim, you know, if you could, make these things super hydrophobic so water just goes off while the material breathes. And then, you know, we don't want it to be fire resistant. We want it to be totally fireproof. And we want it to be good enough for the soldiers, but we don't want it to change the material so that it has just the exact same feel that it had before, and so the kids can wear it for pajamas. So we've done that. Okay, and it's going through a little registration process, and we do that working with the Chief Science Officer of the Army and people like that, and then we bring it to the consumer markets. And it takes a while, and obviously we patent all these things as well. Then they say, you know, while we're at it, let's fix the body armor, because, you know, in a way, we're operating like we're back in the 1600s. And just in case you don't know what our soldiers are up against, there's some body armor here. This is the current body armor, and I'd love for you to pick that up. I'll put it down here when I finish in a minute, because our soldiers, besides trying to be mobile, run in 100 degrees or whatever, they're also carrying about 160 pounds worth of body armor on them. Then they got all their ammunition, they've got their guns. So it's a real challenge to move from that to this. And then, of course, everybody wants Iron Man. So one of the things we're working on are incredible coatings at 12 microns thick that we deposit in a nano way, so we can take the weight of this down, way down, and we can make this truly indestructible. So those things are happening every day, and the way you do that and get it to that point is from a nano engineering side, to where you're literally able to like almost a lizard, you're able to create these slidable plates that are nano-engineered, that are made out of ceramics as opposed to steel, that are always there. And if you get shot, you know, you literally pull that out where it was destroyed, and literally they're lightweight enough and put in new ones, and then just keep going. And by the way, through nanoelectronics, you know, the next generation will be able to say, hey, look, it's bleeding there, so let's administer an anticoagulant, and while we're at it, an antibiotic, so he or she can just keep going. As a finish here, I want to show you the making of a particle. And this is something we do, and we didn't invent the actual concept of this. It was invented by a very, very, you've probably heard of him, Einstein. And in Einstein Bose back in the 30s, just before they got a letter from some friends in Germany that said, hey, maybe you ought to be working on this nuclear stuff, and they sent a letter off to President Roosevelt, they were working on what I'm about to show you, except they didn't have the electronics, they didn't have the power. Inside our new next factory, we're putting an entire substation. It does take a lot of electricity to build these. So this is a nano machine as well. We call it Element X. We talked earlier about how you're able to create literally a new periodic table. And in Element X, you've got what are reactors. This is very much from an Einstein age, except you can see on the front there's a controller. So we're able to control things from an IT standpoint. On that blue machine is literally sucking out of what's behind it there, which is the reactor or chamber, all the atmosphere. So we basically recreate outer space. And inside there, it drops the temperature down to about minus 500 degrees, and there's no chemical, no substance, no oxygen. And at that point in time, we start quenching it with different types of chemistries so that we can downsize current technology, like whether it's gold, copper, or for instance, aluminum, which I'm going to do right now with this. This is inside. We heat it up on what's called a goalpost, which is a copper block. It's 500 degrees below zero inside there. And suddenly, we put that little copper in that wire, or in this case it's aluminum wire. You can see the drop come off because it's sensing the heat. And you see this plume. That plume right there is trillions of nanoparticles. And because of the science we have with that controller, the IT component, we're able to literally control the morphology, the size, and the coating of every one of those so that we begin to create materials that never existed on the planet before. And aluminum that was aluminum suddenly changes into something else that would be basically solid rocket fuel capable for NASA the next day. It takes about 5 hours. Buy the aluminum at Home Depot, send it to NASA. So this is nanoparticles at work right here. So you see nanocopper up there, you see flex circuits and so forth. Nanocopper has a much higher conductivity rate. It can take a lot more heat, no different than what we can do in silicons. We were talking agriculture earlier, and so fields that have been over-harvested, over-cropped, you can take the mineralization of selenium down at nanoscale, mix it with water, spray it back on, and you'll not only get a great field, research shows, but you'll also not need in the future fertilizers, herbicides, insecticides. We've always heard about copper tone, so one of the big things in the industry is creating a new generation of makeups that are safe, and then make our hospitals so safe that literally microbes and bacteria, the bad kind of bacteria, just can't exist, but we do it very, very safely. But then again, always remember this. At the atomic level, it's changing so fast that we keep up with it in a lot of ways. One thing we do is safety, safety, safety. Everything we make at our factories, we make and we ship out after they're nano-engineered and nano-manufactured. It's no longer nano size. So we never ship nanoscale anything, whether it's coatings or what have you. It's totally binded, and by the time it ships out, it's not even nano anymore. But you could have never done it if you didn't nano-engineer it. And that leaves us with a really, really neat world to have a lot of hope, a lot of future, and I'm just excited to be a part of it. And I want to thank Eric for thinking all this stuff up 25 years ago. Thank you.
When you get down to these atomic scales, don't you have problems with quantum effects that you wouldn't have in the mechanical world? So although you were drawing parallels between the two, I wonder if you have problems that you have to solve that we wouldn't have to solve if we were just making a real gear that's the size of your hand.
So clearly a very, very fundamental question. Quantum effects on that scale are very powerful for electronic systems. Electrons are light, wave function spread out. That's what defines the size of the atom. It's responsible for the chemical bonds that hold molecules together. But once you've gone up a level to actually looking at how the atoms move, the electronic interactions basically just apply forces. And the standard approach to modeling these systems in the molecular sciences plots the path of the atoms using classical mechanics, the same as we describe the motion of the planets. Instead of gravity, though, you have intermolecular forces. There are some quantum effects, but you don't notice them unless you go to very low temperatures or look very carefully, and the effects are almost indistinguishable from being slightly higher temperature with higher thermal fluctuations.
How far away do you think we are from those little machines going in and killing cancer cells in real patients?
Well, there are a range of technologies on the latter. Jim described some of the progress in nanotechnology where people are making increasingly sophisticated nanoscale particles. There's a nanomedicine program at Oxford, for example, and many other places, where a drug molecule is small and simple and you dump them into the body and they go everywhere. But if you can package a lot of molecules into something on the scale of, say, 100 nanometers, now you can have molecules that do targeting, molecules that recognize that it's time to open up the package, and then other molecules that do something, so multiple functions. In terms of the kind of technology that I was describing, though, you have to climb a ladder of technology of using machines to build better machines, starting with soft biological materials, using those to build higher quality materials, and so on, until the work starts to look like mechanical engineering, starts to get very clean and understandable. And as for the length of time, well, that depends on people and not physics. I can do calculations on the physics and chemistry, but not the time. I think that it depends very much on how soon we see the emergence of a field of molecular systems engineering, building on the molecular sciences where people just don't think that way today. We need a new way of thinking in those fields.
The quantum dots already exist. The quantum dots are already being used in tests. Some of those are very, very secretive. Started off in plants. You can take it and inject it in plants. You can have the plants literally, if you want, in the backyard, glow at night and things like that. And while that doesn't seem medicinal, it's basically the same concept. And that was the early stuff, and that's about 10 years old. So it's literally where quantum dots, we basically simulate atoms. We can load those, we can discharge those, we can make them inert, so when they leave the body, literally you urinate them. And so that is being worked on, and billions are being spent right now on that. So the biggest problem, the biggest hurdle, which is a good hurdle, it will be the FDA. And so you'll see a lot of this stuff that's already been worked on come out of Europe first, but it's coming at a very fast speed because we've learned how, with the apparatus and with the properly trained people, to make those things.
You just mentioned the FDA. What are the dangers of nanotechnology? And is the FDA even qualified to pass on the safety of this technology?
Yeah, it's a great question. Yes, they are, and so is the EPA, and they have nanotrade scientists, and I've visited with the EPA many times on this. The fact is that there are controls in place. Typically, in terms of shipping right now, you can't ship below 100 nanometers. So when you're in your factory and you're building things, you've got to build it in there at that scale perhaps, but it has to ship out, it'll have to be above 100 nanometers. That's kind of the only rule. One thing to know is there's nanotechnology everywhere out there today. I mean, your clothes are being made with nanotechnology and so forth. As I mentioned, there's never been a single lawsuit in nanotechnology to date. Nanotechnology's been around about 30 years. Now, it will pick up a lot in speed. We need to have governance. We'll continue to have governance in that space, but like all of our factories, I mean, if you read the back of what you're typically lubricating your car with today and you see the materials in it, in most of the cases, what nano's going to do is it's going to take out the bad stuff that you really don't want, like ZDDP, and replace it with things that come from nature, like canola oil, and you're going to see things that you were used in body armor, like bromine, that is just horrific, replaced with a type of silica product and so forth. So it really is less is more, and it is, in most cases, it's safer. But that doesn't mean that we don't have to always be on alert, and it does need governance, just like anything we do in terms of new science.
So the 100 nanometer limit, is that because of tissue penetration at the smaller levels?
Yeah, perfect, John. It's the dermal penetration is typically at 100 nanometers. You know, if you're doing cosmetics and you're below 100 nanometers, you're going to be out of business because, you don't want that. And you're able to converge and assemble a variety of different ways, nanotechnology, to where what you built down in that 20 to 80 nanometer, by the time it ships, it's up into 300 nanometers. It's even, some of our stuff is at 12, 18 microns. But you couldn't have done it if you didn't nano-engineer it.
A lot of this is in the range of what you'd call toxicology as a problem. And there's a challenge here. Ordinarily in toxicology, you have small molecules, they're distinct, perfect entities in their way. With nanoparticles, they're large enough that they're complex. You can have many very similar but somewhat different particles, and their properties depend on their surfaces and so on. Often it's a mixture. And so toxicologists have faced the problem of the difficulty of defining just what it is they're studying. And they've made a lot of progress. I think they're doing good work, but it's a somewhat different challenge from ones that are faced in the chemical industry.
Can you give us your view of the worldwide competition in this area? Where do you think we will be now?
Yeah.
Where do you think we'll be in the future? And what do we have to do differently to keep an advantage?
It's scary because, we're not a state-run, country. I'm not a state-run company, don't want to be. But look at Solyndra. Everybody was like, God, they spent $500 million making solar, right? And they lost, and they went out of business. And that seems terrible until you hear that China gave 5 companies $5 billion each. And then suddenly they reduced the price of solar to where that company couldn't compete. So it's truly global competition, and we're going to have what's called public-private partnerships, more than we've ever had, where the government does intercede, help companies like Tesla and others, and hopefully get paid back. But at the end of the day, in order to compete in a world where you're running up against state-run countries that have enormous and growing scientific capability, some of which are out literally, trying to buy it from us, like Russ Nano. We're gonna have to move fast. We have every government agency working on this right now to create a competitive advantage. We've had an act, the Nanotechnology Act, to speed things up. But we will be challenged more on this than perhaps anything other than the atomic world, that what we face there in terms of both growing it and being first mover to develop some of these products, some of these technologies. And then the unfairness, the cyber warfare that you hear about all the time. And so you spend millions of dollars of investors' money, your own time, and the next thing you know, people are literally trying to steal that. In China, we don't even patent. We patent around the world, but in China, we don't even bother to write a patent.
Thank you.
Take a historical view on this and some of the great revolutions. The agricultural revolution of the Neolithic, there were certain areas that got there first and spread. And you look at the composition of people in Europe, and it's pretty clear there was an advantage to agriculture. The Industrial Revolution started in Britain and gave a huge advantage to the West, which reshaped the balance of power in the world. The Information Revolution was heavily weighted toward the United States. But many people have commented that if you look at the pattern of investment in R&D and broadly competence in various areas of nanotechnology, it's relatively balanced between the US, Europe, and Asia, with Japan being a big player and China being large and growing quickly in this area.
So I like just one quick last irreverent question I want to ask, and I want a quick answer from both of you. How much does science fiction inform what you do?
Well, when we came up at Motorola with the StarTech, which was a big-time seller, and it was fun to be involved in all of that. I mean, that came from what? Star Trek, the communicator, and so forth. So, God bless science fiction writers, because ideation, thinking it up, that's the science fiction phase almost. And then invention, where you actually go to invent it. And then the hardest part, innovation, where you got to make it work, and it work every time, which means building assembly lines that have repeatable quality control, scalability. That's called execution. And so, but it does start with that incredible out-of-the-box eureka ideation.
My mother read me hard science fiction novels when I was learning to read. Anybody read Hal Clement? Has a lot of chemistry and physics in his books. Mission of Gravity, by any chance? It's the first book I can remember reading. Any event, so I was sort of raised with science fiction, which gives a perspective which says the future is broad and open and likely to be surprising, with enormous technological change. And starting with that frame of reference and then getting very reality grounded at MIT leads to interesting places. I will say that more recently in nanotechnology there has developed a huge mythos of little tiny machines that run around and maybe will eat you. And that has been a major problem because it has nothing to do with anything anyone wants to build or plans to build, and has very much confused the discussion of both what is possible, how to do it, and what the real risks are, which I think are mostly in the domain of arms control.
Thank you.
Thank you.
Thank you.